Good morning. So we're going to talk more about momentum conservation today. Hopefully give you some tools that'll be helpful for solving homework problems. But we can take a second here and try and debug what's going on. So it works for one of you, but Bryce, you're just seeing it's not loading. So we can give it a minute too to see if we get get a few more students. Can you guys hear me? Shoot. Hi, Carolina. Yeah, at least it will be recorded, so yeah, maybe it's an issue with your connection. Um, we'll have it recorded, of course, so you can review it if it doesn't show up, or maybe check in a few minutes and see if it cooperates then. So, okay. Uh, does anybody have any questions or concerns before we get started? Besides, connection issues. Or I should say, everybody else's, your connection is working okay. Um, so, the first thing that I wanted to mention today was a clarification about something that came up yesterday. So I kind of led you astray a little bit. I think Carolina had asked, how do you know? Uh, let me pull up the question. um, oh no, that's not the right question. One moment. We had worked on this question yesterday about two pucks, and the question was, how do you know that this is a one-dimensional collision? And I had given you some response like, oh, if it's only moving in one dimension to begin with, blah blah blah. That was not right. So upon reflection, the thing that should jump out to us as a flag, and I didn't think of this until after we had talked about this, was the the thing that lets us know that this is one dimensional is the language head-on collision. So this tells us that the objects are gonna hit symmetrically, just head on, so that it should be constrained to one dimension. Oh, that's not a nice picture. So if you see that language, that is a red flag to you to know that it's a one-dimensional problem. As opposed to what could happen if you don't have a head-on collision is imagine like trying to shoot pool or something. And you hit the balls head on if you want, to just get the cue ball to hit the ball that you're looking at straight. But if you wanted to, go at an angle, you hit it not head on. So kind of the conceptual picture is, let me try and draw this a little better. If you hit it head on, then it's going to be constrained to one dimension. But if you don't, if you hit it like offset, right, then you could get a situation where one is going one way. Let me see. Let me try and indicate this. Then you could get a situation where they're going off at angles. Now, the thing is, this will have the same x momentum final as this initial situation. You know, where this has but in the y direction, you know, there's no momentum in y. Well, there will be no momentum, no total momentum in y final either. But what that means is just that the components for each have to sum to 0. Or the components for when you combine them together are going to sum to 0 in the y direction. So, and we'll look at a problem that's just like this today, where we have two-dimensional collision and we work through it. But that's the thing that I wanted to point out, is this, to clarify. The thing that lets you know that this is a one-dimensional collision is that they tell you that it's a head-on collision. Anyway, so sorry for misleading you yesterday. It's sort of similar to things where we see language that's like, you know, initially at rest or something. It's sort of a clue that can be, and sometimes those clues are really important pieces of information, but they can be subtle to pull out of the text. So, and that one eluded me yesterday too. So I wanted to make sure that that was clear. Yeah. Yeah, there's a couple, there's a complicated problem in the homework that deals with 2D collisions. It's a tutorial problem. And those give you a lot more sort of guidance. So, okay, let's look at some example questions. Yesterday, I think I told you the next thing that we were going to get into was this one? No. This one? What is going on? Wait a second. Sorry. Just having trouble with my clipboard. Can't find the question. Ah. Okay, here we go. This is what I was looking for. So we'll look at a couple more collision problems. And this is a good one. Yeah, yep, that pendulum problem is one of the tutorial, I think is one of the tutorial problems. Or I'm thinking of, are you talking about the ballistic pendulum? I'll mention that one today. That's a really good problem. It's kind of like this problem, actually. Reminder to myself. We'll mention the ballistic pendulum. So here's an inelastic collision problem. So we have a sports car, a 930 kilogram sports car collides, rear ends a 3,000 kilogram SUV stopped at a red light. The bumpers lock, the brakes are locked, and the two cars skid 2.8 meters before stopping. A police officer, estimating the coefficient of friction between the tires and the road to be 0.8, calculates the speed of the car at impact. What is that speed? No worries regarding connections. We'll get you straightened out. Yeah, I mean, there's some gremlins that live on the internet. I just, you know, the thought has crossed my mind, man, if the internet was much less reliable, we would be in so much trouble in terms of our ability to communicate. So I'm just glad that it works as well as it does, as much as it does. And if, you know, if it's not cooperating for you, Bryce, we can meet. We can get stuff figured out if you have questions. So don't apologize for it. It's not your fault. Anyway, so with regards to this question, I would tell you this question. You know, a lot of our textbook questions are kind of canned, are kind of silly. But this is actually like a real question. So or a plausible question, I would say. I was on a jury a few years ago, and it involved like it was a car accident related situation, and they had witnesses, expert witnesses that came in and talked about doing this kind of analysis to figure out, you know, how far, you know, you can figure out things like how fast the car was moving initially. So this idea is not a made-up idea. It's a real legitimate kind of problem, which I think is kind of cool. So let's set it up. So the first thing I would do is let's draw ourselves a little picture. We've got a sports car. Ultimately, we want to figure out how fast this thing was going. Initially, all we know is its mass. And it's going to crash into an SUV. Now, the mass of this thing is 0. It's at rest. And it has, or sorry, the velocity, the speed of this thing is 0. And it has a mass of 3,000 kilograms. And so kind of what, you know, this is before, then they crash into each other. You know, whatever, however we indicate a crash. And at that moment, let's call this the velocity after they crash together. Now this is an inelastic collision. So, you know, because they're sticking together, so we're not going to conserve energy. But we will conserve momentum. And then kind of the third part is, you know, this combination is going to slide some distance. And we're given that distance as being 2.8 meters. And we're also given that the, you know, the police officer estimates that the mu k, coefficient of kinetic friction, sliding friction, was 0.8. So here's kind of the setup. So the other thing, yeah, I'll just indicate here, this is an inelastic collision. So momentum will be conserved, but not kinetic energy. And we know that immediately because they stick together, so it's perfectly inelastic, was the terminology, or completely inelastic. So let's break this up into basically stages. From here to here, we can make use of energy conservation, or sorry, momentum conservation. So I'll label, I feel like it's helpful to kind of label this in parts. And then from 2 to 3, we're not talking about momentum conservation. Instead, we're going to talk about energy conservation. We have some initial kinetic energy. When I say initial, I mean initial after they are stuck together. And we're going to convert that into work that's done by friction. Okay. Okay, so a lot of these more complicated problems. So I was looking through the survey responses so far with regards to what people were concerned about with the final. And somebody had made a comment that they thought that one of the things that's difficult about this kind of stuff is combining ideas together. So I think this is a really good problem to look at because it is asking us to combine some things together, both momentum conservation and energy conservation. And for the same reason, this ballistic pendulum problem is a really excellent one because it's kind of the same situation. You conserve momentum in an inelastic collision, and then in that problem, you convert that momentum, or not momentum, you convert the resulting energy of the combined masses, kinetic energy, into potential energy stored in gravity. But it's sort of a two-step situation: momentum conservation and then energy conservation. This is the same situation. This problem is also that. It's two steps. We have momentum conservation and then energy conservation. Are there any questions about the setup so far? Yeah, so then if you think about it, after the collision, the mass will become, the mass total will be ma plus mb, if you want to think about it that way. So let's show ourselves that. So if we look at momentum conservation, we're going to know that the initial momentum is going to have to equal, yeah, exactly. So the energy is not conserved during the collision, but that kinetic energy that results from the collision that we get from momentum conservation is going to be spent doing work with friction. So that's part of what makes this question difficult, or these kinds of questions. But do you see how it's similar, Caleb? You were talking about the ballistic pendulum. It's kind of the same idea. You take that initial part, the first part of it is sort of a momentum conservation question, and then the second part is an energy conservation. So let's break this down. The momentum initial is going to have to equal the momentum final. Well, actually, let me, instead of initial and final, let me use 1 and 2, just so we see the steps. The momentum initial, MAVA, and that's going to have to equal MA plus MB times BA plus B. Okay, so we have this. Let's call this like equation 1. And then from energy conservation, what do we know from energy conservation? Well, the kinetic energy at 2, and we could state this, let's write down all of our pieces, just so it's sort of familiar, even though many of these are going to be 0. But just for sort of continuity. So recall, when we've had situations where there are non-conservative forces present, like friction, our general energy conservation expression, we're going to have the kinetic energy plus potential energy initial, i.e. mechanical energy, is going to equal the kinetic energy plus potential energy final, And if there's mechanical energy missing, then we say that it's we can surmise that that's gone into work done by non-conservative forces. So for us, we don't have any potential energy in this question. So the initial and final potential energy are going to be 0. We're going from moving to stopped, so we're also not going to have any kinetic energy final. So all we're going to equate is the kinetic energy at 2 to the work that's done by friction is the non-conservative force that we're talking about. Kinetic energy, recall this is 1/2 mv squared. Well, the mass that we're talking about is going to be the masses combined together. And the velocity that we're talking about is the velocity after they collide. And that's going to equal the work that's done by friction. Well, what's the work done by friction? That's the force of friction. It's F dot D in general. We're along a line, so i.e. the force of friction and the distance are aligned. So I should be more diligent about indicating the force of friction, but it's opposing the motion always, recall. So it'll be the force of friction times our distance, which I called x up above. And what's the force of friction? Remember, the force of friction is the normal force times mu k. In this case, since we're talking about sliding friction, the normal force. So what's the normal force? If we have an object that's just sitting, or it's not on an angled surface or anything, or not on an incline, we can get this from doing Newton's second law in the y direction. So remember, we would have the normal force minus mg equals 0. So just to review here. So the normal force, in other words, is mg. Need that ingredient. So mu k mg. So we'll need that in here. So 1/2 m v squared is going to equal mu k. Now our m, recall, this is going to be the masses of both as well, because they're stuck together. So mu k m g, so that's the force of friction, and then our distance, x. So now we have an expression that has the velocity of the combination, and we've related it to mu k and the distance. So we could pull out from that, we could solve, in other words, for the velocity of the combination. Now notice the mass actually drops out. It appears on both sides. So let's solve this then for v a plus b. So we would multiply over by a factor of 2. 2 mu k g x. And then we would have to take a square root. So at this point, we know the velocity of the combination, and we can use equation 1 to relate that to the velocity of the car initial. So from equation 1, we have this. So let's solve this for VAB. Okay. Yeah, it is. Krishna, that's what we found here. The force of friction is the normal force times mu. So now we can take this expression for VA plus B, and eliminate it in our other expression. So in other words, we have MA BA equals our root 2 mu k gx. So now we have an expression that has everything that we know and contains VA. We can solve it for VA, i.e. the initial velocity of the car. So we'd have to multiply, divide. So it's going to scale our the piece that we got from thinking about energy conservation. So let's put in some numbers. So let's see, the car was 930 kilograms. The SUV 3,000 times 2 times 9.8 times 0.8 times 2.8, blah, 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 blah. So you crunch those numbers, you find that the initial velocity was 28 meters per second. So what we've done, we've connected together momentum conservation in an inelastic collision, and then the motion that results from that. We've looked at energy conservation to figure out how far it'll go. So, and this is, just for reference, this is like 62 miles per hour, which is a very reasonable speed when we're thinking about, cars and stuff like that. So, questions about this question? What questions do you have? I feel like this is a relatively complicated question, so I want to make sure it's clear what we've done. Yeah, this is relevant to the Ballistic Pendulum tutorial. It's kind of the similar type of two-step problem. Let's see. I have a question. Well, why don't we plug... oh, so all we're doing is... yeah, probably. So those are good questions. So we're not plugging it into equation 1 so much as we're basically combining steps together, right? So if we took here, we could solve this for VA plus B. And then if you know what VA plus B is, you could solve for VA. Would be another way to think about it. Like if you know VA plus B, you could, from equation 1, see that VA is going to be MA plus MB times VA plus B all over MA. So we just kind of combined everything together. But you could break it up into pieces if you wanted to. Yeah, I think that is a pretty high coefficient of friction. Um, there's all kinds of circumstances that could influence this sort of thing. Like if you recall back in the when we talked about friction in chapter 5, if it was like the road surface was wet or something, you could get a lot different mu k. So it would have a big impact potentially on your ability to stop and stuff like that. So it's kind of interesting. It's interesting too. You guys know, like in that vein, uh, snow tires. You ever messed with snow tires compared to like all season tires or whatever? They are like noticeably softer, and that's because, and it kind of agrees with our notion about how they're going to need to have a higher coefficient of friction. So like race tires too, I think are really gummy or kind of sticky by comparison. It makes sense. Um, okay, so I really want to show you a two-dimensional problem because I think that's going to be helpful with the homework. So, and I've been sort of teasing about this the whole week, but it took us a little while to get to this point. So let me show you a 2D collision. No, not this one, if I can find it. This one? Okay. So this question is good. This is a sort of a prototypical momentum conservation question. So let me read it to you. 2D momentum conservation. So this is question 54. A billiard ball of mass 1.130 kilograms moving with speed VA strikes another ball initially at rest of mass MB equaling 0.135 kilograms. As a result of the collision, ball A is deflected off at an angle of 29.5 degrees with a speed of VA being 2.4 meters per second. So let's set this up. We have mass A. It has some initial velocity. It hits mass B, which has a slightly larger mass, which is at rest, so it has a velocity of 0. And then after, so they hit, there's a collision, however we can draw a collision. And after the fact, VA moves off at an angle 29.5 degrees. VA prime, so the velocity after the collision is 2.4 meters per second. And VB prime, we don't know, nor do we know the angle. And maybe it would be less confusing here if let's indicate it like that. So let me just move. Here. So is that setup clear? Oh yeah, because the question, for whatever reason, it's the, you know, the question must have got chopped off or something. We want to find VB prime theta B. Um, yeah, it's kind of a, I don't know. I must have omitted part of the text or something. So this is an example of 2D momentum conservation. Uh, we want to find, like I said, we want to find VB prime theta B. So for two-dimensional momentum conservation, it's the same conceptual. It's the same conceptual idea as what we've been doing for 1D, i.e., the sum of the momentum has to equal the sum of the final momentum has to equal the initial momentum. But now we have 2 dimensions instead of 1. So what does this look like? Well, it's very similar to how we approached Newton's second law. So if we had components of forces that were in x and y, we would sum the forces in x and y, and then we could find accelerations in x and y. So now in this situation, we have momentum in x and y. So we sum the momentum, look at conservation of momentum in x and y, and then we can come up with equations. We can solve that system of equations for our unknowns. So in this case, our unknowns are the velocity and angle of or the speed and the angle of ball 2. So I would recommend being pretty methodical about it. So let's look at the momentum in x first. So in the x direction, and I should really have a coordinate system here. In the x direction, the initial momentum, we're going to have ma va is going to equal, after the collision, we have ma va prime. Now this is at an angle, so we only want the component that's along the x-axis. In other words, we want ma va prime cosine theta. In addition, we'll have mb vb prime cosine theta b. So that's our expression for momentum conservation in the x direction. Oh, and I should say, this is an inelastic situation, if that was not clear. Ugh. Let's look at momentum in the y direction. So initially, there's no movement in the y-axis, along the y-axis, or along y, up or down. So this is 0. Let me just write this. So in other words, we're looking at p in y. So it's going to be 0 is going to equal ma va prime sine theta. So the y piece here, plus mb vb prime sine theta b. And so now we have 2 expressions. We've got an equation from the looking at momentum in the x direction and looking at momentum in the y direction. It's inelastic, so we don't have the ability to look at energy conservation. But we have two equations and two unknowns. We're trying to find the velocity VB prime and theta b. So in other words, we're going to need to take something from, eliminate some one of our unknowns. We could try and eliminate theta, although that's kind of tricky because we would end up with stuff like an inverse cosine of stuff, which looks kind of messy. So let's do it this way. There's more than one way to go about this, but let's try this. We're gonna solve for VB prime and then substitute it in. So eliminating VB prime, and then we can get the angle out. So from this second one, you can see we can solve this if we subtract the sine theta piece, divide by MB, divide by sine theta B. This allows us to pull out VB prime. And then let's take this and sub into 1. So if we do that, what do we have? We have MA VA going to equal MA VA prime cosine theta plus MB, and then we'll substitute it in here, negative MA VA prime sine theta MB, sine theta B times cosine theta B. So we've eliminated VB prime from our system. And then we can simplify things a little bit. There will be a factor of MB that's going to cancel. And then also notice we have cosine theta over sine theta, so we can consolidate this a little bit. So I'm going to subtract over. Recall, we're looking for, our quantity that we're trying to extract out of here is going to be theta b. So let's simplify this and work towards getting it by itself. So notice we'll have cosine theta b over sine theta b. That's cotangent theta b. So this allows us to get our theta b into one term, or one factor of it. And then we could solve this for theta b. So we would have to divide this stuff by this. AVA prime sine theta. And then we would have to take an inverse cotangent to undo the cotangent. So now we have an algebraic expression for theta b. One note about this. So we could, compute this. One detail that I want to draw your attention to is when we set this up, theta b was below the axis. So as we've put it in here, we've talked about this as being just sine. But actually, we're gonna want this to be a negative quantity because it's below the axis. So we can compute this here. So if we're looking at our picture up here, in order for these to cancel, the cosine components, it doesn't matter if it's above or below the axis, they're still going to be in the same direction. The sine components, though, that's going to need to be a negative number. So when you go and compute this, you get a positive quantity, you'll have to make it negative. So if you crunch the numbers, we put in our masses and everything, you find that this is 53.9 degrees. So, but negative 53.9. Getting at this, and we often do this where we're not as careful about the sign because for some, a lot of things it doesn't matter if you're talking about the cosine components, but the sine components it does because they have to add to zero because remember there was no initial momentum in the y direction. So that's sort of a detail with this question in particular, and it reminds us, to be mindful of the sign of your components. Okay. But now notice if we have theta b, we can put this into the substitution that we made above. And when we do that, we find that this is 1.4 meters per second. So that's our solution. Theta b 53.9 degrees, VB prime 1.4 meters per second. So I think this is a good example. It gets at some of the subtleties with working with angles. More importantly, it's an example of a question in 2 dimensions with momentum conservation. So that's an excellent question. Yeah, if your calculator can't do the cotangent, then what you could do, so that's a good point. So if you had something that was cotangent of, x equals like a over b, what you could do to avoid having to mess with the cotangent is that tangent is 1 over cotangent. So you could flip this thing over. And then do the inverse tangent. It should work. Yeah, that's a good point. So sometimes I do a lot of this when I do your homework and stuff. I'll do it in MATLAB. So another alternative is, if the calculator doesn't have that functionality, use a computer. But yeah, that's an excellent point. Students have run into problems with stuff like that, like if we're doing an exam and they're less familiar, like it turns out, oh, you can't easily evaluate some inverse trig function or something. That can be annoying. So yeah, that's a good question. Other questions about this? So like I said, I think a lot of this stuff is conceptually it's not so bad, right? We're just conserving momentum in x and y. But where you can see where this got more complicated is with the algebra. So other questions? What questions do you have? And of course, there's some stuff like this in your homework where you have to deal with. So I really wanted to show you one more. So I realize we're basically out of time. Let me show you one other really quick example of momentum conservation in 2 dimensions. So check this question out. So I feel like I don't want you to think that these questions are all complicated. Potentially. I mean, basically, Carolina, what I was talking about with that is just that there's more than one way to substitute in. Like a lot of times when you have these systems, rather than us substituting in let's see here, rather than substituting in from 2 into 1, we could substitute in from 1 into 2, etc. There's different ways to go about it. But yeah, I'll think about that. Or what I might do is just do it differently in the second section, so you can see. If you look at that one, there will be a different method. But let me show you this last question. This one will only take a minute. So we have an inelastic collision between 2 objects of equal mass, each having initial speed v, and then the 2 move off together at speed v over 3. And the question is, what is the angle between their initial directions? So this one is kind of cool, I think, so I wanted to show you. So we have 2 objects moving at v. They collide into each other. They stick together and then move off at speed v over 3. So, and the question is, what is the angle between them? We could call that theta. So this is another example where if we look at the momentum conservation, if we look at the momentum conservation in x and y, in y, there's no, they're going to have to sum to 0, but it's symmetrical, so we can see that that's going to work out. But in x, we would have each has mass m. So the initial momentum in x would be mv cosine theta. Or actually, let's use theta to represent the whole angle and phi to just represent half of the angle. So mv cosine phi plus a contribution from the other one, cosine phi, is going to equal 2m. Remember, they stick together, times v over 3, because now they're moving off together, that combined mass. Yeah. So I just wanted to show you an example of, just to kind of make the point that these aren't all so complicated. Some of it is just setting stuff up. So you add these together, you'd have 2mv cosine theta, or sorry, phi, equals 2mv over 3. Notice, like, everything cancels out. You have cosine phi is 1 over 3. You do an inverse cosine. You find that phi is about 70.5 degrees. So if that's half of the angle between them, then theta would be 141. So this is just another example, a short example. Sorry, I didn't mean for us to go over time. But I just wanted you to see another example. Since they take so long, I figured, or since the algebra can be kind of involved, I figured it'd be nice to have another one that's really short, just to show you kind of another setup. So, I don't want to go too much longer, but any other questions? So, yeah, we will. So, of course, if you run into questions with the homework, so the 141 is the fact that theta is phi plus phi. So if phi was 70 and a half, then you just add, it'll be 2 times that. So, yeah, as you're working through the homework, I anticipate there being some questions because this, like I said, the algebra can be kind of complicated. So if you have questions, contact me on Teams, reach out, shoot me an email. We can start a discussion in the homework section on Teams. That seems like a good way to go about it. That way, if people have the same question, we can kind of work on it together, which is nice. So, and sorry I went a little bit over, but don't hesitate to contact me with any questions, and we will see you tomorrow, potentially, if you haven't had lab already. Otherwise, have a nice, an excellent weekend, and we will see you next week.